Welcome to College Algebra. This is going to be an experiment in many ways this year, but today is my first attempt to record with this. Since my wireless mic has not received its new battery so that it'll work, I'm having to record this with my computer only, so hopefully you are picking me up well enough. Today's lesson is very, very short and sweet, but it's a touch to get us into the mood, ready to do some math again. Okay, I just needed to catch on a couple things with you. The first part of this is the simple sets of numbers. We've been bugging you with them for years. We keep adding more sets to your list, but you've seen all of these before. The first set that you learned back in elementary school, first set you ever learned is, of course, how to count. And you begin counting with 1. So the natural numbers are the set of numbers that begin with 1 and go 1, 2, 3, 4, 5, 6, 7. Okay. However, in mathematics, we never want to write all that out, so we use symbols to represent them. In a textbook, these would be bold-faced. In handwriting, we attempt to bold-face some of them, but essentially the natural numbers would be a capital N. It's not going to let me write on where I typed, so we'll put those out here, I guess. So capital N is your naturals. The whole numbers are nothing more than adding 0 to the list. And of course, they make sense too. They're capital W. It's once we get to the integers, one of the ones that I have the most trouble getting students to remember. And integers, I always remember integers with a Z on the end because we use the letter Z to represent the integers. The rational numbers and the irrational numbers sort of go together as a pair, because they're actually opposites of each other. If something's rational, it can't be irrational. If it's irrational, it can't be rational. Okay, unfortunately, the rational numbers have several ways to define what's a rational number. Rational, you'll notice in the word rational, there's ratio. Ratios are written as fractions. So if you can write a number as a fraction, it's rational. The other way we look at rational numbers is by their decimals. If you turn a number into its decimal value, rational numbers will either terminate, such as 4.325, or they will be repeating decimals, such as 7.6354, with, say, the 5-4 repeating every time. So rational numbers have to repeat, or they can be written as fractions, something like 2/3, or even the number 4 is rational because it can be written as 4/1. Now, who remembers what rational numbers use for a symbol? Can't be R because we know the real numbers get the R. So rational numbers for I guess, I don't actually know this for a fact. There could be 2 reasons. Q is really close to R, but Q also stands for quotient, and since rational numbers are written as fractions or are quotients, there might be a relationship there. I can't actually tell you. I know the historical reason for why Q was picked. Okay, on the other side of things, we get the irrational numbers, and they do indeed get to be the letter I, and they are simply your non-terminating, non-repeating decimals. So it can simply be a decimal that goes on 8.76389 and has absolutely no pattern, just keeps going forever. And then, of course, there are some of our favorite irrational numbers. Of course, pi and our good buddy e are all irrational because they are non-terminating, non-repeating decimals. When you put those all together, when you put the rationals and the irrationals together, you get the reals. And of course, we know we write the reals with a double-lined R to make it look bold-faced. But they are all the rationals plus all the irrationals when you put them together in one big set. And you'll notice Naturals, wholes, and integers are all rational. So basically, reals are everything we wrote above this line. Everything from here up, those are all reals. But in Algebra 2, we disabused you of the notion that all numbers are real numbers because we introduced you to the imaginary numbers. And imaginary numbers are simply the square roots of negative numbers. The square root of -4, which we all know to be 2i, or it doesn't have to break down nicely. It could be the square root of -12, which would be 2i square root of 3. So you can have those types of numbers. Anything with a square root. The key thing is it's square root, not cube root, not fourth root, not 10th root. Imaginaries are only square roots of negative numbers. That's important. Last but not least then, somebody said, well, hey dude, let's put the real and the imaginary numbers together and we're going to form a complex number. So complex numbers are always numbers written in the form a plus bi, where a is the real part and bi is the imaginary part. So a complex number is any number that can be written in that form. Something like 9 minus 4i, that is a single complex number. That's one number. But so is 8. 8's complex because it can be written as 8 plus 0i. And by the same way, 3i is also complex because it can be written as 0 plus 3i. So in reality, all numbers are complex numbers. So you have a little matching thing on your assignment where you simply have to, they give you some example sets of numbers and you have to match which name and symbol do they go with. I guess I skipped that fact. Complex numbers are of course written with a capital C. The imaginary numbers don't actually have an official symbol other than we use that lowercase italic I to represent the imaginaries. So that's the first part of your assignment. The other part takes you back to the joys of Algebra 1. And in Algebra 1, one of the most fun things you ever learn to do is everybody's favorite, word problems. Now, don't panic, we're not doing word problems today. The biggest trouble with word problems is people have to learn to translate the words into mathematical symbols. So we are working with how do you translate words into symbols. And in this case, it's just practicing that skill. Now that you're significantly older than you were when you took Algebra 1, hopefully this will appear very common sense. Okay, the first couple have you trying to write these phrases. They're just simple phrases that we're writing into sentences. We'll also be looking at some other examples later on where we actually have to translate them into actual equations. So in this particular case, we have 4 less than triple a number. Okay, you have to answer, think about what the word means. 4 less, okay, well probably you're going less. Less means subtract. So 4 less than triple a number. How do I triple a number? I triple a number by taking it times 3. Pick any variable you like to represent your number. In this case, I'm going to use n for my number. So if I triple my number, I have 3n. The question is, am I doing 4 minus 3n or 3n minus 4? Well, 4 is less than the triple number. So the triple number's there, and you are going less than that by 4. So it would be 3n minus 4. Second example here, the sum of a number and 7 is squared. Anytime they say a sum, you know you have to be dealing with two things getting added. So the sum of a number and 7, that part has to be happening first. This time I'm saying I'm going to use x for my variable. So x, the sum of x and 7, well that's no problem, we know how to add those two, is squared. Well, what's squared? The 7's squared or the sum is squared? Well, it's saying the sum of is our prepositional phrase, so the sum is squared, which means then I need to put quantity squared on it. Okay, the quotient of 50 and 8 more than a number. Okay, quotient, hopefully you're screaming, quotient, that's divide. So I have to divide the quotient of 50 and 8 more than a number. So I know it's division. It's the quotient of 50 And says that's my second part. 8 more than a number. Well, how do I get 8 more than a number? My number is, say this time my number is P. 8 more than that would be P plus 8. Okay, the last one, I actually want to add something onto this one. I should have added it earlier. 3 times the difference of a number and 5 increased by 9. I want to put also on there is 11. So add that to the sentence. 3 times the difference of a number and 5 increased by 9. Well, okay. 3 times what? You know it's 3 times something, so we're multiplying. 3 times the difference of a number and 5. Okay. So the difference of a number and 5, difference would be subtract. So I have to put this in parentheses because 3 is times the difference. So I'd have to go, difference of a number and 5 would be something like x minus 5. Then it said increased by 9. Is 5 increased by 9? Well, once again, English and punctuation in this case, there's a comma. So you did 3 times the difference of the number and 5. Now it's supposed to be increased by 9. So we would need to, increase would be add 9. And then the big key thing here, I want you to learn about setting up equations. Is 11. Anytime in math, if you're translating one of these, the verb, in this case is always the equal sign. So the verb equals equal. Wherever you find a verb, boom, slap the equal sign in there. If you will learn that thing, you will never have trouble translating these. Because find your verb. Sometimes it's is, sometimes it's something else. Wherever they put the verb, that's where you put the equal sign. That's a critical idea. Okay, so here are a few where we can actually practice that with sentences. The length of a rectangular line is 3 feet more than twice its width. Okay, now in this case, we have to have variables here. The length of a rectangular line, so kind of makes sense, doesn't it, to make L be the length, is 3 feet more than twice its width. So probably makes pretty good sense to make the width BW. The length of a rectangular line is 3 feet. Translate the words. The length of a rectangular line. So length is verb. Look, scream, verb is. So the length is equals 3 feet more than twice its width. What's more mean? Add. In this case, since you're adding, it doesn't matter what order you do it in. So we can go 3 more than twice its width. Well, twice the width, of course, is 2W. You could also write that as 2W plus 3. They would both be correct. Okay, to make that a little more exciting, try the second one here. Kate's score on her chemistry test was 37 points lower than twice the score on her history test. Once again, we need variables and representative so we can keep straight what's what. So we have Kate's score on her chemistry test, so I'm going to make C be the chem test score. And then she had a history test, so let's do H for history test. And yeah, I know this isn't writing too exceptionally. I'll work on quality here later on. Kate's score on her chemistry test was 37 points lower than twice the score on her history test. Okay, we usually have trouble with 37 points lower. Where do I go with the lower? You don't have to worry about it. The words are telling you in order. Translate the sentence. Kate's score on her chemistry test. What represents her score on her chemistry test? C. Then we hit the all-important word, was. So therefore, equals. Okay, it's 37 points lower. So lower means I'm going to have to subtract. So do I do 37 minus twice her history test? Or is it twice her history test minus 37? Well, it says it's 37 points lower than twice your test. So you'd have to start with her test first, her history test, twice her history test, and then go 37 points lower. People have a tendency to want to take the chemistry test and subtract 37. Stop and ask yourself if that's logical. Which was the higher score? Which was the lower score? It's common sense, but the sentence, the grammar of the sentence tells you what to do. Okay. This last one's a little trickier. In 3 more years, Miguel's grandfather will be 6 times as old as Miguel was last year. Okay, so that one's going to take a little bit of thinking about. So the question is, what are our variables? Eventually, probably this problem would eventually ask you how old are they now. So, assuming we add that in there, I'm going to do G is grandpa's age now. And M is Miguel's age now. So it says, in 3 more years, Miguel's grandfather will be, find that verb, will be, right there. There's the equal sign. So how do I do before that? In 3 more years, Miguel's grandfather. So how old will Miguel's grandfather be in 3 more years? Well, if he's G now, he'll be G plus 3 more. 6 times as old as Miguel was last year. Okay, the equal sign we put there. So how do I do 6 times? Well, obviously 6 times as old as Miguel was last year. Well, how old was Miguel last year if he's M this year? Last year he was M minus 1, and of course I have to put that in parentheses to take it times 6. And there you've translated the words into symbols. Let the English tell you what to do. Believe it or not, English and math have a tie-in. Okay. Go off and enjoy these wonderful, exciting problems.